Well, hey everyone, and welcome back. So first off, I'd just like to apologize for a small spot of glare that you'll see somewhere around here. It's just that I'm recording this video slightly later than I would usually, and it's pretty dark outside, so I had to use some additional lighting available in my studio, and I use that term incredibly loosely. But anyways, into our actual topic for today, folding. So you may have noticed that right here I have a fault drawn, a 2D cross-sectional diagram of a normal fault, which seems slightly strange, but this is to help us get into the point of folding, because faulting and folding are similar in that they're both types of deformation that can occur to rock. So faulting occurs, you'll recall, due to large amounts of pressure over time that cause either the footwall to be thrusted upwards, the footwall to be thrusted downwards, or for the two to move horizontally relative to each other, which would be a strike-slip fault. So faulting can be a result of compressional, pushing together, tensional, pulling apart, or shear forces. Meanwhile, folding is different in that it is always a result of compressional forces, always a result of rock being pushed together. It's also different in that faulting can occur, the only real condition for faulting to occur is high pressure, right? Faulting, if I can write, hope this marker's not dying out. Faulting is high pressure. However, for folding to occur, we also need high temperatures. So it's slightly different in that respect. They're both types of deformation, but since at higher temperatures the rock will deform more malleably, or sort of like modeling clay. If you were to compress it together, it'll more like fold. It won't just, like, say for example this ruler. If you apply much more strength to this, then it'll just snap, right? Meanwhile, folding is, the rock behaves more like you would expect modeling clay to, where it just sort of bends either upwards or downwards, and there's no sudden burst of energy that snaps it, and you get that brittle deformation of a fault. So with that out of the way, let's get into actually looking at a simple diagram of a fold. So we'll go with our old reliable two-dimensional cross-sectional diagram. So let's say we've got something like that. And then we've got something, we got some folded strata that's clearly been folded downwards. And we'll put one more up there, why not? And we'll label these A, B, C, and D. So originally, by the law of original horizontality, we know that these must have been lying just flat. So there must have been some compressional forces combined with a relatively high temperature. So this piece is likely taken from deep within the Earth. This, in this case, isn't the surface line. It's just the edge of the scope of this cross-sectional diagram. But we have high pressure and high temperature, and that caused these to push themselves just inwards there. Now, this particular type of fold, when the crest down here is pushed downwards and the limbs open upward, that is known as a syncline. Syn as in synergy and cline as in incline. Syncline. So you can just identify that, as I said, by opens upwards, like a parabola, just sort of, or like a U shape. Opens upwards, and if you want to look at like the arrow piece of it, it sort of points downwards. Okay, so that's a syncline. Easy enough. However, there's also a second type that should make plenty of sense, and that is called an anticline. Now, anticlines are incredibly similar, but guess what? They're the opposite of synclines. You're going to see We'll label these again, A, B, C, and D. And there's a layer up here too, we'll just call that X. You're going to see that the layers are deformed upwards such that they point upwards. I'll draw a little stress arrows again. The anticline is where they are deformed such that they push upwards instead of downwards. Well, the crest points upwards and the limbs open downwards. So that is anti, as in anti-anything, I don't know, antichrist, anticline, and cline once again as in decline. And these are just the opposite. They open downwards and point upwards. Point upwards. Now, pictures of synclines and anticlines will never be this simple. This is an incredibly limited view. And I'll give you an example of something where we'll see both, and this is a concept you have to understand. We separate these two but as different types of folds, but often they're both pieces to the same folded structure. So we'll have a slightly bigger cross-sectional diagram here. We'll say there's the boundaries. And let's say we've got some, maybe the top layer isn't folded, just to put that into perspective. And what we actually usually have looks sort of like a sinusoidal function, where you kind of go like something like this, of folded strata down here, and you'll get something just like that. Just these lines going in and out, and then there's some erosion here making an unconformity. And we'll put one more in there. And then we'll just label these. A is our top, B is in here, that's B as well. There's C, D, E, F, and G is our little one poking through in spots down here. So as you can imagine, when you fold rock, if you've got an incredibly long distance over which you're folding, it's not just all going to go uniformly upwards. It's going to sort of crinkle. You can imagine sort of compressing, I don't know, for once I'm at a lack of metaphors, maybe just like crumpling a paper together. It'll have all these little ridges where they kind of bend in different directions, or maybe pushing a piece of tin foil together such that it compresses. Just imagine compressing something that requires very little force to do so. And it'll behave similar to that, where you have pieces that are bent upwards and pieces that are bent downwards, all within the same strata of rock. So once we've mapped this out, we can define our synclines and anticlines. Here's our anticline. All this strata, we can say that's an anti. I'll just abbreviate that, anti. And then down here, there's our syncline. And then we've got another anticline here. Another syncline. And then we come up to another anticline by the very end. So it really does just look sort of like a wave here, and you can kind of think of them, if you're looking at these, the anticlines will be where the crests of the waves are, and the synclines will be where the troughs are. Now, there are a few more pieces I want to talk about. One, I just want to mention, I don't have a surefire way, any really clever method of remembering which is which between syncline and anticline. The most clever thing I've thought of, which is still quite unsophisticated, is just that, well, the anticline looks like this, right? It's going to look something like that, which I think of anti, and then I look at the first letter A, and then I just sort of, you know, it looks like you can draw an uppercase A in there. If you look at this piece right here. I don't know. Just remember it in any way you can. Maybe you can just remember anticline dips downwards, syncline dips upwards. I don't know, I think this one's just kind of funny. A for anticline. And now, the final piece, in general, folds, and these aren't the only two types of folds, by the way. We've been sticking mostly to the basics here for this first video. But the pieces that you'll see in a fold, actually, I don't really want a 2D diagram for this. We'll just have a simple anticline here. Let's just say it looks like that. There are some universal pieces to a fold. You've heard me mention these before. The top of it or the bottom of it can be called the crest. And then on each side of the crest there is a limb, a right limb and a left limb, which are the pieces of the strata that dip away from the crest, either downwards or upwards if it's a syncline. And then there's one final piece I should talk about, which is the axial plane, which in the two-dimensional world we can just kind of look at that as the line that divides the two, that runs through the crest, that sort of splits it down the middle, at least when it's a symmetrical fold like this. And it's not just a line, though. We do have to specify that it is the axial plane because in the real world we live in more than 2 dimensions. And an actual fold will sort of, extend out like this, and we'll have this, more 3-dimensional look to it. So the plane will actually stretch out and it'll be running, carried on till the end point. Even if I don't have enough room. But just understand that this is in 3 dimensions, and the plane refers to the surface that runs between the front at the crest and the back. And those are the big points, the universal points for all folds. There are many other more complicated ones to talk about, but this has just been a basic introduction, how folding occurs, high temperature, low pressures, compressional force, types of folds, synclines and anticlines, synclines open upwards, anticlines open downwards, and some basic pieces of a fold that you will see in all folds no matter what. So yeah, hopefully this was informative, otherwise good review. Hope you guys enjoyed, and I'll see y'all in the next video. Ciao.